Right, so in this class, we will talk about linear programming duality. This is a last lecture of a linear programming class. So duality is a very key concept in optimization. There are different forms of duality. For example, the most common they use is so-called Lagrangian duality, which is what we will use to derive linear programming duality. But actually, there are different ways to derive linear programming duality. There are more mathematical treatment of it, but we will just use Lagrangian dual since it's more intuitive. And we will also use Lagrangian dual to derive other forms of duality. For example, for nonlinear programming and for mixed integer programming, we will keep introducing how do you apply Lagrangian duality to those different problems. So if you have never heard about duality before, just a very intuitive concept, right? If you think about optimization as optimizing over primal variables, right? AI less than or equal to b, minimizing C transpose X, right? So remember in the previous lecture, we talked about at the optimal solution, there can be n active constraints, right? Having known that there are n active constraints, you can think about duality as a way of pricing the n active constraint, right? In other words, how much price are you paying to satisfy each of these n active constraints? So that's what we will use to motivate duality here. So if you have taken a calculus class before, probably you have heard about this concept called Lagrangian. So let's give you this very simple optimization problem. This is what's in the linear programming textbook, where you only have two variables, right? So this is a general concept, not just applied to linear programming. So I gave you actually a quadratic problem, where the objective is minimizing x squared plus y squared subject to a single linear constraint, x plus y equals to 1. Right? So this is a quadratic objective function subject to that x and y lies on a single line here, right? So you could introduce this concept called Lagrange multiplier P. The idea is saying, let's forget about this constraint, right? So if you forget about this constraint, of course, you are sort of relaxing the problem, right? Because you leave one constraint out. What you can do is you pay a price for violating the constraint. So this P, you can think about this P as a price of violating this single constraint. Now you change the problem to the following form. This is called like a Lagrangian function, where you have the original objective plus P times 1 minus x minus y, right? So this term is the violation of the constraint, right? If you violate that constraint, you pay a price P, right? But now let's assume you pick an arbitrary P. Okay, yeah?
Is P just a scalar?
Yeah, P is a scalar because you have one constraint, yes. Okay, so while keeping P fixed, you can minimize Lagrangian over x and y. Right? So let's say if you violate the constraint, you pay a price P. But then you can still minimize this Lagrangian function by setting the partial derivative with respect to x and y to 0, since this whole thing is a convex function when P is fixed, right? Because x squared, y squared, take the Hessian of this function. It's nothing but the 2 times the identity matrix, right? So the optimal solution to this unconstrained problem is x equals to y equals to P, right? So now you may be wondering, it depends on P, but P is just a scalar you pick sort of randomly, right? You don't know what will be the good price to pay if you violate this constraint. But for this example, it gives you a very intuitive way of calculating the P, because if you want to satisfy the constraint x plus y equals to 1, then with this additional constraint that gives you p equals to 1, and the optimal solution to the original problem will be x equals to y equals to 1 over 2. Right? So this is just an intuitive way to think about this problem. Maybe you have heard about this in your previous calculus class, right? So you can think about P as penalizing the violation of the constraint, but then if you combine this with the original constraint, you get the solution to this problem. Right? Actually, we will generalize this idea when we talk about nonlinear programs. Okay. Yeah. So this slide is just to give you a sort of intuitive understanding of what is a Lagrangian. It is nothing but you pay a price for not satisfying the constraint. And there is a way to determine what would be a good price to pay. Okay. So let's talk about Lagrangian dual for a general linear program. So let's consider a linear program in standard form where we have ax equals to b and x greater than equal to 0. Right? So here let's say similarly consider a penalty for not satisfying this equality constraint ax equals to b. Right? So recall that there are m constraints, so I pay a price, let's say p belongs to Rm, right? For the violation of each constraint, you pay a price p sub I. Right? In total, there are m constraints. Okay. So now let's consider this function called Lagrangian function, which is nothing but you pay a price for not satisfying this constraint. So that in total, the price you pay is p transpose times b minus ax, right? Now, even if you pay the price, you still want to find the x that minimize this whole objective, right? Because since this is a minimization problem, you have a penalty term here, but then you still want to find the minimum over this Lagrangian function. Okay. So an interesting observation here is this Lagrangian function will always provide a lower bound of the original problem. Right? So that is a key observation here. Does anyone see why that is the case? Because I did not write it out explicitly in words, but you can try to think about why no matter what value of p you pick, this term will always be a lower bound of the original problem.
So we are minimizing the original problem.
Mm-hmm.
Minima will always be less than the original.
Yeah, exactly right. So since you are minimizing x greater than or equal to 0 over this function here, right? So the x you pick, so let's denote the x of this minimization problem as x hat, right? So x hat minimizes this function, right? Now, so x hat is, let's say, the minimum of, let's say, this particular optimization problem. Just this particular problem here, okay. Now, let's denote the optimum of this optimization problem as x star. Okay, right? Of course, since x star is the minimum of this optimization problem, but it may not be the minimum of this problem, right? Right, because if you plug in x hat here, it minimizes this whole expression, right? But x star is a minimum of a different optimization problem, right? They may be the same, they may be different, right? what you do know is that if you plug in x star here into this expression, it cannot be better than x hat, right? Since by definition, x hat is the minimum of the function you are trying to minimize, right? Okay, so that's why if you plug in x star into this expression, it must be greater than or equal to the original problem, the problem you are minimizing over. Right? Is it clear? Here. Okay, so now let's plug in x star, which minimizes this LP, right? Now what do you get? Because x star minimizes this particular problem, x star satisfies ax star equals to b, right? So this term will go to 0 because you have b minus ax star. So this term go to 0, you are left with C transpose x star, right? So what is C transpose x star? It is the optimal objective of the original LP, right? Okay, so in conclusion, no matter what value P you pick, right, it's independent of which value of P I pick, this function GP will always be less than or equal to the original objective value. Okay, so that is an argument where you can see the GP provides a lower bound of the original LP. So as I said, GP is P is given arbitrarily, right? But then what will be the most interesting value of P you want to pick, right? Since you know no matter what value of P you want to pick, that is a lower bound of the original problem. The more interesting P you can pick is to choose the value of P that provides the tightest lower bound of the original problem, right? Because you want to get a bound that is as close as possible to the original problem. That is where, if you pick an arbitrary P, it might be a trivial problem, right? So that is also one of the applications of duality, right? Let's say when you solve an optimization problem, let's assume if you have limited resources, you don't necessarily want to solve this problem to optimality, right? So what you do want to know is how far you are from the best possible optimal solution, right? So in practice, what duality gives you is also an estimate of how far you are from the optimal solution, right? So you cannot, for a given P, you cannot get better than this function GOP, right? So even if you haven't converged, right? Even if you haven't reached a point where the reduced cost is greater than or equal to 0, as long as the solution you get is very close to this function GOP you got, right? Or the maximization problem here you can also terminate, right? Maybe you can afford to have 1% optimality gap, then you can stop, right? So that's another application of duality in practice. Okay, so I want to make sure everyone understands this key concept, why the function GOP is a lower bound, and why we are striving to get the tightest lower bound as much as possible. Right? Hopefully it is clear. Any questions? Okay. So now, in the next slide, I will derive the Lagrangian dual of an LP. So I don't want to overwhelm you with that slide. So let's write it down step by step. Okay. So recall that GOP is a lower bound, right? It is nothing but minimize x greater than or equal to 0, C transpose x plus P transpose B minus AX. So let's evaluate this problem, right? What this gives you. So first I'll recognize that P transpose B doesn't depend on X, right? So you can take P transpose B out. So you have P transpose B plus this minimization problem. So now we have, let's say, C transpose minus P transpose A times X. Okay, so we end up with a linear function of X. Right? And you are trying to minimize over a linear function of X where X is greater than or equal to 0, right? So how do you write down this function in a closed form? Right? It's minimizing a linear function. The only constraint is X greater than or equal to 0. Right? So first of all, let's think about one case, right? When is this minimization problem unbounded? X is greater than or equal to 0 here. And then you are minimizing. Right. So minimizing and then being unbounded means this term equals to minus infinity, right? So when will this term go to minus infinity?
When the expression in the bracket is not 0.
Is not 0. Does it make a difference if it's greater than or equal to 0 or less than 0? Since X is greater than or equal to 0.
So we have X, yeah, then when it's
yeah, less than 0, right? So you only need one entry of this vector to be less than 0 for this to be unbounded, right? So if only there exists one entry of this term that is strictly less than 0, you can pick the corresponding X for that entry and set X to plus infinity, right? And then this whole thing goes to minus infinity, right? So you could write down this term as okay, so in order for this term to be bounded, all the entries has to be greater than equals to 0, right? So you can write as maybe write it in column vector A transpose P. No. Let's say C minus A transpose P has to be greater than equal to 0, right? So when all the entries are greater than equal to 0, if you want to minimize this term, you should let all the X equals to 0. Because all the entries are non-negative, so this will be equal to 0. Otherwise, if there exists one component of this vector that is negative, then this will be equal to minus infinity, right? Okay, so otherwise. Okay, now remember, our goal is to find the value of P such that this G of P provides a bound as tight as possible. Right? So we are maximizing over, so remember, the goal is to maximize over G of P, right? Such that you get a bound as tight as possible. So since you are striving to get the tightest lower bound, right? I would argue that you could ignore this case, right? This case is uninteresting to you, because if in this case, if it falls into this case, G of P will go to minus infinity, right? You don't want to provide a lower bound that is minus infinity. It is uninteresting to you. So we are, if you are deriving the dual of an LP, we would only be interested in this case, right? Okay. So therefore, the dual of an LP is written in this particular form, right? Remember, in this case, this term goes to 0, but you are still left with P transpose B here. You have a question?
Yeah, I was kind of wondering, so we went from minimizing C transpose minus P transpose A.
Yeah. Uh-huh.
We have C minus A transpose B.
Uh-huh.
Is there any reason why we got rid of the transpose and like the C and then?
Oh, yeah. So because I just take the transpose of this whole thing. This is a row vector, right? Usually we write a column vector as C, right? So C transpose is a row vector.
Okay.
Therefore, I take the whole transpose of this row vector, right? So if you take the transpose as C minus A transpose P greater than or equal to 0, you can also write this condition as C transpose minus P transpose A greater than or equal to 0 transpose. Right? So usually when you write a vector, by default, we assume it's a column vector.
Okay.
Right?
Gotcha.
But then now this whole thing is a row vector. I want to write it in a column vector form, that's why. Okay, yeah. All right. Now, let's say if we fall into we fall into this case, then the constraint P needs to satisfy R. You can write it as A transpose P less than or equal to C, right? Or alternatively, if you prefer row vectors, you can write it as P transpose A less than or equal to C transpose. Any of these cases are fine, okay? And the objective is P transpose B, right? Since if you fall into this case, this minimization problem goes to 0, you are left with P transpose B, okay? So now as you can see, the dual of a linear program is also a linear program, right? The number of variables you have in the dual is equal to the number of equality constraints you have in the primal problem, right? So remember the dimension of P is equals to the dimension of the constraints in the primal, right? And then now the number of constraints equals to the number of variables in the primal, right? So remember C is the same dimension of X, right? So then the number of constraints is same dimension as the number of variables. All right. Well, that's nice, right? Now primal is an LP, the dual is an LP. As you can imagine, if you want to solve an LP to optimality, right? A very naive approach, actually you don't need to do that. I will show you how the primal variable is related to the dual variable later on. So a very naive approach you can do is you run simplex algorithm on the primal problem and the dual problem in the same time, right? And the primal problem gives you a feasible solution. The dual problem gives you a bound, right? How far you are from the best possible solution you get. Okay, then if the solution you get from the primal is close to the bound you get from the dual, you can terminate. You don't have to wait until the primal gives you the global optimal, right? Let's assume you have a super large LP with maybe 1 billion variables. You cannot afford to solve it to global optimality, right? So then you can use this approach. So this approach is used even more often for nonlinear problem. For linear problem, it's not necessary to run primals and dual simplex at the same time, right? I will show you why later. Okay, so this is basically what I just derived. I want to make sure people do follow this rationale here. But now if you have a different form of an LP, you can follow exactly the same procedure. So let's assume the primal constraint is in this polyhedral form, right? AX greater than or equal to B. Right? Instead of in the standard form, you write everything using the inequality constraint. Now, the tricky thing here is if you have an inequality constraint, in order for the Lagrangian function to provide a lower bound, you need the Lagrangian multiplier to be greater than or equal to 0. Okay, so here, as you can see, I'm penalizing the violation of this inequality constraint, right? Since AX is greater than or equal to B, Okay, so this b minus ax will be less than equal to 0, right, if x is feasible. So if you want to use the same argument we used before to show this Lagrangian function is always a lower bound, then better pick p to be greater than equal to 0. Because if you want it to be a lower bound, then this term multiply the p transpose should be less than equal to 0, right? If you want to use the same argument we used before, showing that if the solution is primal optimal, GLP gives you a lower bound, right? Remember let's go back a little bit. What argument did we use? The argument we use is x hat is a minimum of this particular Lagrangian problem, but x star is an optimal solution to the original LP, right? And then we plug in x star and shows that when x star is the optimal solution to the original problem, this whole thing goes to 0, right? And if you want to show, use the same argument, we have to make sure that this whole thing is less than equal to 0 in order for the lower bound argument to hold. Okay, so therefore we need to pick p to be greater than equal to 0. And similarly, if you have a less than equal to constraint here, then you need p to be less than equal to 0. Right? So that's a rationale why we need to restrict the signs of those Lagrangian multiplier. Okay, just so that you multiply with this constraint, it is less than equal to 0, it provides you a lower bound. Okay. Now, okay, so the other tricky thing here is in this problem, we do not restrict x to be greater than equal to 0, right? So you already dualize all the constraint here. Then x is unconstrained in this minimization problem, right? So if x is unconstrained, you have to force this whole vector to be 0, right? If you have one of these, one element in this vector to be non-zero, you can always make this whole thing unbounded. Right? Okay, so that's the two difference we have because the signs in the constraint change, then the constraint on x has changed, right? And then the corresponding dual will also change, right? So here, as you can see, you have an equality constraint in the dual, and then you have a greater than equal to constraint on the dual variables. Okay, so this is a subtle point here. Okay, now you could try to derive the dual for different form of the LP and just follow the proofs, the steps of the proof we have already gave you as an exercise, right? But then after you have done the exercise, if you want to get the dual of the LP, you can refer to this table here. Okay, I would not suggest you to try to recite the table, right? Each time you forget about how to derive the dual, then just follow the math to derive it again yourself, right? Don't try to recite anything here. But then this table is a nice way for you to check if your derivation is correct. Okay. So how do you actually use this table? So as you can see, this is a primal problem in a very general form. They are greater than equal to constraint, less than equal to constraint, equality constraints, and some of these x are greater than equal to 0, some of them are less than equal to 0, and some of these x are free. Right? So you have all sorts of constraints and all sorts of variables in the primal, right? And then recall that the size of the p, the dual variables, should be consistent with the size of the constraint, right? In order for Lagrangian to be a lower bound, right? So if you have greater than equal to constraints, the corresponding dual variables are also greater than equal to, and same wise, right? Now, as for the size of the dual constraint, they are the opposite signs of the primal variables. Okay, in order for the dual to be bounded, right? Otherwise, they provide a trivial bound. Okay. Again, you don't need to recite this. Just revisit this proof, and you will get the same result. Okay. And there is a quick exercise you could use as a practice. Okay, to give you an LP, then you can take the dual of the LP. All right. Now we have introduced the concept of the dual of given linear program. So in the next few slides, we will show you some properties of a dual. Right. So these properties will, it will give you some deeper understanding why do you need the dual and so forth. Right. So now, let's first prove this property called weak duality. Right? So it says if X is a feasible solution to the primal problem and P is a feasible solution to the dual problem, then the dual objective is a lower bound of the primal objective. Right? Okay. So let's think about why this is true. Right? First of all, remember when we construct the Lagrangian dual, we pick the signs of the P such that no matter what P you pick, this GLP function is the lower bound of the original problem. Right? Now, I give you one more condition is that this P is a feasible solution of the dual, right? Because any P, for any P you pick, the GLP is a lower bound. Of course, if you pick a feasible P to the dual, that will provide you a lower bound of the primal problem. Okay? So this is almost by construction, right? By the way we construct the signs of this vector P, the dual will provide a lower bound of the primal. Okay. Now maybe we can write it down in a sort of a more rigorous way, and then you could get the gap from the dual as well. Okay. So to show the math, let's define two sets of variables. Okay, one is ui equals to pi times the i's constraint a transpose x minus bi, right? So this is nothing but you multiply each of the dual variable to the constraint in the primal, right? And then Vj equals to Cj minus P transpose Aj Xj. Okay. So by construction, we know that all the ui's are greater than or equal to 0, all the vj's are greater than or equal to 0. Right? So this is by construction because if you go back to the slides, the way we pick the signs of the pi variable is that it is the same sign as the primal constraint, right? And the way we decide, the signs of the dual constraint, it is the sort of the opposite sign of the primal variables, right? And the reason is because we want to keep the dual problem to be bounded, right? As you can see here. Now with that, let's compute the following values. If you sum over all the ui's, right? You could do the math. This is nothing but P transpose AX minus P transpose B, right? And similarly, if you sum over all the Vj, this is nothing but C transpose X minus P transpose AX. Right? Now, if you calculate the sum over I ui plus sum over j vj, right? Of course, it is greater than or equal to 0. Now, these two terms will cancel out, right? You have a P transpose AX minus P transpose AX here. So this is nothing but C transpose X minus P transpose B. Right? So as you can see, now you derive the C transpose X minus P transpose B is greater than equal to 0. So the reason I want to write this down is because I'm going to use the UIs and VJs for another proof later. But now, in order to understand weak duality, the proof is very simple because the way you construct the primal and the dual already give you weak duality as taken, right? Yeah, so this is sort of a typed proof. Now, what does weak duality imply? Right. So there are some corollary you can get from weak duality. They are as follows. So the first corollary says if the optimal cost in the primal is minus infinity, then the dual problem must be infeasible. Right? So when you read this, it can be a little bit counterintuitive. But then if you write it down, it is very trivial because you know the primal problem is a minimization problem, right? And the dual problem is a maximization problem, right? And we know that the dual provides a lower bound of the primal, right? So if the cost in the primal is minus infinity, right? As you can see, the dual problem is a lower bound of the primal. If the primal problem is minus infinity, the dual objective must be minus infinity, right? Since it is a lower bound. So this implies the dual objective is also minus infinity, right? So what does a maximization problem's objective being minus infinity mean, right? You have a maximization problem, now I'm telling you the objective value is minus infinity. Right? That means the maximization problem must be infeasible, right? If there exists a feasible solution in that maximization problem, then the objective must be not minus infinity, right? It will give you either a plus infinity or a finite objective value, right? And same thing what you can do, if the optimal cost in the dual is plus infinity, then the primal problem must be infeasible, right? This is following the same logic. Okay, so now there is one more corollary to weak duality. So let X and P be feasible solution. All right, okay, yeah, without looking at the proof, right? Let X and P be feasible solution to the primal and the dual, and suppose the primal objective equals to the dual objective, then X and P are optimal solution to the primal and dual respectively. Right? So can anyone give a very simple argument why this is true?
It's like the dual is lower bounded than
Yeah.
the dual problem.
Yeah.
If you find like where they're equal,
Yeah.
then that should be the point where.
Yeah, exactly. Yeah, you already said that. Yeah, yeah. If you since the dual is a lower bound of the primal, right? That means the primal cannot, the optimal solution of the primal cannot get better than the dual. Right? If they are equal, that means that they must be optimal. Right? Okay. So now you may be wondering, right? We already have strong duality. We already have weak duality. When does so-called strong duality hold, right? When you solve the primal problem and the dual problem, when does that hold, right? So actually for linear program, strong duality hold, right? Also actually, in general for convex problem under some what is called constraint qualification, strong duality also hold. Okay, now, so the theorem is saying the following: if a linear program has an optimal solution, so when we say a problem has an optimal solution, usually we mean it's neither infeasible nor unbounded. We just have a finite optimal solution. Then its dual also has an optimal solution, and the respective optimal costs are equal, right? And the other way is also true, right? Because the dual of the dual is a primal itself. You can try to show that, right? So if the dual is feasible and bounded, then not necessarily has to be bounded. But if it has a finite optimal solution, then you can show that the primal also has an finite optimal solution, and the gap is 0. Okay. So how do you prove this theorem? I'm not going to show a complete proof because a complete proof is quite difficult. We will just use what we discussed in the previous lecture. Recall what is the optimality condition of the simplex algorithm? Right? What condition do you check when you decide to terminate the simplex algorithm? There is some criteria we need to check, right? When if you hit a basic feasible solution, and you check all the basic feasible directions, right? And what terms is greater than or equal to 0, then you know the basic feasible direction cannot improve your objective value, right? What is that that concept we talk about on Tuesday? Is it too hard to answer, or is it too simple to answer? You think I'm too stupid to ask you this question?
Reduced cost.
Yeah, right, exactly right. So if the reduced cost is greater than or equal to 0, remember what the reduced cost means is if you move for one step using this basic feasible direction, the objective will change by the reduced cost, right? So therefore, if the reduced cost is greater than or equal to 0, you know that particular solution is already optimal, right? Because you try all the basic feasible direction, they are not going to improve. Okay, yeah. So then, as I said, there is a very deep connection between the reduced cost and the dual, right? Actually, you can show when the reduced cost is greater than or equal to 0, it provides you a dual feasible solution to the dual of the LP. So that's what we will show next. But in order to do that, we need to make an assumption saying that when you have a primal optimal solution, there always exists a solution that gives you the non-negative reduced cost. It's not always the case. Remember, the other way is not always true, right? When you are at an optimal solution, not always you will have non-negative reduced cost because there are some solutions that are degenerate, right? But then you can assume there is some versions of simplex algorithm which always will give you an optimal solution that has non-negative reduced cost, right? So that's an assumption we are going to make here. Yeah, so let's revisit what we talked about in the previous lecture, right? Recall that this is the standard form of the LP, and the basic feasible solution is you choose a basic matrix, and then XB is B inverse times B, and Xn equals to 0, right? The non-basic solution equals to 0. Assume you can always get such a solution with non-negative reduced cost, right? So this is how you calculate the reduced cost. Then let's define a vector P, right? So P equals to CB transpose B inverse, right? So this does occur in the reduced cost, right? As you can see in the formula of the reduced cost. Then you can show P is a dual feasible solution just by plugging this value to the dual constraint. Okay, so if you plug in this constraint, then you have P transpose A less than or equal to C. This is nothing but the condition that the reduced cost is non-negative. Okay, you could do the math yourself. Then if you calculate the objective of the dual and the objective of the primal, what you will get is the dual objective equals to the primal objective if you set this to be the dual variable. Right? You could check that is the case. Therefore, you do have a primal solution and a dual solution, which give you exactly the same objective, the strong duality hold. Okay, but of course we need the assumption that at the optimal solution, you do realize the reduced cost is non-negative. Okay. All right. So with that, let's talk about the possibilities of primal and dual. When I study linear programs, I always get confused about, when is primal problem infeasible, when is it unbounded, what happens to the dual, and so forth. So this table can be very useful to help you understand all the possible scenarios that can occur when you have a primal LP and a dual LP. Right? It doesn't matter the rows are primal or the columns are primal. It's the same thing, right? Because there is a symmetry here. Okay. Now, one instance you already understand quite clearly is the first instance here, right? Whenever the primal has a finite optimum, we already proved that strong duality hold, right? So whenever the primal or the dual is feasible and has a finite optimum, strong duality tell you when primal has a finite optimal, the dual must have a finite optimal, right? So this is the only whenever one of these has a finite optimum, only the finite optimal is possible for the dual, right? Now, the cases when the problems are unbounded and infeasible are much more tricky, right? So first of all, let's talk about the unbounded case, right? So remember, we have this weak duality theorem, right? So whenever the primal is unbounded, right, or the dual is unbounded, the other must be infeasible, right? That's what weak duality tells you. Okay, so if one of these is unbounded, then the other must be infeasible. Right? That's the only scenario that can occur. However, there this particular case where both primal and the dual can be infeasible. Right? So this can occur from time to time. Right? Okay. And how do you certify a problem is infeasible? We will show you a theorem at the end of this class. Okay. So whenever you get confused, you can refer to this table here. Now, okay, so now let's talk about a concept called complementary slackness. It's less frequently used for linear programs, but then if you study general nonlinear programs, this is a concept that will be used. So what does that mean? Okay, that means let X and P be feasible solution be to the primal and the dual problem. Then let's assume X and P are optimal solutions. Then these two conditions has to hold, which is Pi times AI transpose. This is the Lagrangian multiplier, multiply the primal constraint, right? So you can think about the second constraint as the primal variable multiply the dual constraint, right? So by design, we know that all of these terms are greater than or equal to 0, right? That's sort of by construction. But when would they be 0? What would happen, right? So that's why I show you the previous proof here. Okay, so this is the slide we use to show you weak duality, right? Remember, the U's are primal variable, the dual variable multiply primal constraint. The VJs are the primal variable multiply the dual constraints, right? And by construction, all the U's are greater than or equal to 0. All the VJs are greater than or equal to 0, right? And it happens to be the case that the sum over UI and the sum over Vj represent the difference between the primal objective and the dual objective. Right? So this is C transpose X minus P transpose B. So when is C transpose X equals to P transpose B? Yeah, right. If you have C transpose X equals to P transpose B, that means the primal equals to the dual. Then you have X and P being optimal. Right? And when are they equals to 0? They are equals to 0 when all the U's and all the Vj's equals to 0. Right? What are the UIs and the Vj's? They are these terms, right? So they are called complementarity constraint because you have the dual variable multiply the primal constraint, right? If they are equals to 0, that means whenever the primal constraint holds strictly, the dual variable must be 0, right? That's what it means. At least when UI are 0, at least one of these terms must be 0, right? That's what's called complementary. Okay, so now let's move it back. It should be straightforward to show that. All right, so here's a remark. What is the optimality condition for an LP from a primal dual perspective? What you need is, what you can do is you have primal feasibility, you have dual feasibility, and complementary slackness that give you the necessary and sufficient condition. And a slightly different optimality condition is you have primal feasibility, dual feasibility, and the primal and dual objectives are equal. Right? They are just equivalent. This condition and this condition are just equivalent to each other, right? Because the difference of these two terms are nothing but the sum of the UIs and plus the sum of Vj, right? That's essentially complementarity slackness. Okay. Yeah. Now, next I will introduce another application of a dual variable, right? So as I said, the first application, let's say if you don't really care about the theory, right? Why do you need to study this? The first application of the dual is maybe you cannot solve the primal problem to global optimality. The dual give you an estimate of how far you are from the global optimum, right? That's from an application perspective. Here, there is from the application perspective, there is another way of using the dual variable, which can have a very nice physical interpretation. So the motivation here is, I want to know how much the objective changes when the right-hand side B is perturbed slightly, right? So think about the B as some resource constraint, right? So if you buy, for example, you can have a problem where, let's say a knapsack type of problem where all your resources have to be less than or equal to the existing resources you have, right? Now I want to understand if I get more resources, how much I can improve my objective, right? Or if I get less resources, how much my objective will deteriorate. Okay, I will show you a physical example in the next slide. Let's first understand the theory, how to derive the marginal cost. Okay, is a definition of what I want to do clear. The motivation is that if I change B a little bit, how much my objective will change, right? Okay. So think about the following way. If the problem is non-degenerate, right? If you are at a basic feasible solution, then B inverse times B are strictly greater than or equal to 0. That's what the degenerate solution means. Then if you perturb B slightly, right? So if D is very small, then B inverse times the right-hand side remains to be greater than or equal to 0, right? That remains to be feasible. Now we know that the same basis remains feasible if D is small. But what about the optimality condition, right? You need to keep the reduced cost to be greater than or equal to 0 in order for the same basis to be optimal, right? One important observation is the reduced cost doesn't depend on the right-hand side, right? It only depends on the basis and the left-hand side constraint. Okay, so therefore, P remains dual feasible, right? So therefore, when D is small, B remains to the optimal basis, right? Since the solution is primal feasible and the corresponding dual is also dual feasible. Then the new objective will be, remember this is nothing but the dual variable, the dual times B plus D, which is nothing but P transpose D, right? So the way to interpret that is if you perturb B by vector D, right? D can be a very small perturbation to the right-hand side. Then the optimal objective will change by the dual variable. Okay, that's a way to interpret that. You look confused. Do you have questions?
Why would that be the case? I guess like I'm not seeing the connection.
Saying
Like
the
why P would affect that?
Oh, so this term is the dual objective. First of all, do you buy that the same dual variable remains dual feasible?
Yeah.
Yeah, you buy that, right? Because it doesn't depend on B, right?
Yes, yeah.
And the same basis remains primal feasible if the solution is non-degenerate, right?
Sure.
And then by the strong duality proof we showed you before, right? Then we have the dual still being the dual optimal solution, right? So if you perturb B by B plus D, then the dual of this problem is the maximization over P transpose B plus D, right? Because you perturb the primal by D, right? Then the dual objective is perturbed by D as well, right? My argument is the same dual variable will remain the optimal dual if D is very small. Okay,
Yeah.
right. Therefore, you don't need to change the dual variable you got before you do the perturbation.
Got it.
Okay, yeah. And so what is the same dual variable? It is nothing but this term. We showed that in the strong duality proof. Or you can believe me, the previous dual optimal solution is this term here, right?
Yeah.
Okay. Now, since the optimal dual is still this term, then the change to the objective value by perturbation of D is nothing but P transpose D, right? So you can think about the P as a derivative with respect to B, right? If you perturb B slightly, how do you differentiate this optimization problem with respect to its parameters? Right? If you only change the parameter slightly, how much will the optimal objective value change? Okay. Yeah. So now let's give a very concrete example to help you understand how to interpret an optimization problem, right? So recall in the first lecture, we talked about this diet problem, right? The idea is, let's just suppose you are a poor man or a poor woman who only want to satisfy the basic nutrients while minimizing the cost of food, right? You have like apples, eggs, milk, and so forth, right? You want to spend as little money as possible on purchasing food such that you satisfy your daily requirements of calories, protein, and vitamins. Right? Remember that linear programming problem. Right? The constraint is nothing but you sum over the consumption you have from each food, and then the nutrients you get has to be greater than or equal to the calorie requirement, the protein requirement, and the vitamin, and so forth. Right? So remember the right-hand side parameter B for that diet problem are calories, the requirements for calories, protein, and vitamins, right? Now, how do you interpret the marginal cost here, right? The way you can interpret the marginal cost is the cost you pay for getting more nutrients, right? Remember, what does C transpose X mean in that particular problem? That means the money you spend on purchasing, eggs, milk, apples, and so forth, right? That's C transpose X. And if you interpret that problem from the dual perspective, right, then this dual variable means the marginal cost, the additional cost you have to pay. Let's say if you want to increase the calories by a little bit, how much additional cost you have to pay, okay? And then you can interpret the dual objective as the total cost you spend on satisfying the requirement for the three nutrients, right? Okay, so that's sort of, and then the primal equals to dual. It sort of makes sense, right? And in that problem, you can interpret the dual as the price you paid for getting different types of nutrients, right? Okay. Any questions here?
So when we say like cost paid, you're referring to like how much you paid for the food, like money-wise?
Yeah, so the C transpose X is how much money you paid for the food, right? You spend the money on buying apples, bread, eggs, and so forth. And then the dual price means how much money you spend on satisfying each nutrient requirement. Yeah. So then it must be equal to each other, right? That's just a different way of looking at that problem. Yeah. Now, let me tell you another case where dual variables are used in the real world, right? So the other application is related to setting the electricity price, right? So you may be wondering how electricity prices are set especially for large consumers, right? So you and I are just smaller consumers. You pay your monthly electricity bill based on a flat price, right? But if you think about a big utility company like Duke Energy or big chemical plant, right? How do they pay their electricity bills? Actually, they have to face an hourly variation of electricity price, right? Because the supply and demand will change on an hourly basis, right? Especially now you have more solar and wind, they are highly affected by weather, right? But then how do they decide how much money they are going to pay at each hour, right? The way they pay the electricity bills is based on the dual variables of a linear program. Okay, so you can think about matching the supply demand as a linear program, right? You want to minimize the total cost of satisfying the demand given the different types of electricity generators you have, right? And in that, imagine in that linear program, the demand of each customer is a right-hand side parameter, right? It could be like all the electricity flowing into that customer has to be greater than or equal to that customer's demand, right? But then how are we going to charge that particular customer? They are just charged by the dual variables for that particular constraint, right? Because you have a sum over the flow into that customer to be greater than or equal to the demand. And then the dual variable means how much additional cost you are going to pay if you perturb the demand a little bit, right? Similar as the nutrient problem, how much additional cost you are going to pay in order to get more calorie, right? That's the money you pay for calories. So this is called the economic dispatch problem. That is when LP is really used for solving industry scale problems. Now, I have 10 minutes left to talk about, I would say, one of the most important theorems in linear program. As I said, I believe there is a very important theorem called Minkowski well, right? That means any polyhedral set can be represented as convex Hall of extreme points plus the conic Hall of extreme rays, right? So this is another theorem. I think if you were to ask people what is the most important theorem related to linear program, some of them will tell you this theorem called Farkash lemma, right? It was discovered, or you can also say invented by Farkash. Maybe he's a very humble guy. He called it a lemma, but it's actually a very important theorem, right? So what's the motivation of Farkash lemma? Let's not look at the math for now, right? I won't show you the proof. I just want to give you an intuitive way of how to use this lemma. Okay. So let's suppose you have a system of linear inequalities. Right? You have I gave you some linear inequalities. Right. Now, I ask you the following question: how do you certify this system of linear inequality describe an infeasible set? Right? So there doesn't exist any solution that satisfies all the linear inequality in this set. Right? It is not such a trivial problem because proving infeasibility is saying for all the x you can find, they cannot satisfy all the linear inequality. Right? As you can imagine, when we try to prove something like for all, it doesn't satisfy something. It's a very difficult thing to validate. Right? So how do you give people a certificate saying that if I give you this variable, and then it can prove this linear system is infeasible, right? So that is when Farkash lemma comes into play, where you can see. Now let's look at this theorem and think about how we can use that, right? So it says if A is a matrix of dimension m times n, B is a vector in Rm, then exactly one of the following two alternative holds, right? Only one of the A and B can hold true. So the first, the A is saying there exists some x0 such that Ax equals to B, right? So A is saying that nothing but, this system is feasible, right? And the alternative is to give you a condition where you can show this system is infeasible. Okay. Now, so what is the alternative? So the alternative is saying if this system is infeasible, you can always find a vector P such that P transpose A is greater than or equal to 0, but P transpose B is strictly less than 0. Okay. So now you can interpret P as a certificate of infeasibility. Okay. So now can we see why B is, such a P is a certificate of infeasibility, right? So first of all, the first condition is saying P transpose A greater than or equal to 0, right? So you can think of P as some sort of Lagrangian multiplier multiplied to each constraint, right? You are using these Lagrangian multipliers P to aggregate all the constraints, right? So after you aggregate all the constraints, the left-hand side is greater than or equal to 0, right? And you also know x is greater than or equal to 0, right? So then, therefore, x multiply the left-hand side must be greater than or equal to 0, right? But now, if you look at the aggregation of the right-hand side, P transpose B, they are strictly less than or equal to 0, right? So therefore, P gives you a certificate such that this system has a conflict, right? If you aggregate all the left-hand side constraint times x and aggregate the right-hand side constraint, the left-hand side must be greater than or equal to 0, and the right-hand side is strictly less than 0. Right? So that gives you a certificate of conflict, right? So, but then Farkash lemma is telling you if the system is infeasible, you can always find such a certificate. Okay, yeah. So now you can imagine what happened when you use Groovy to solve an optimization problem, right? And then when the solver tells you this problem is infeasible, what is the solver doing, right? Maybe if it's an LP, it actually finds such a vector P and tells you, find a conflict and tell you it's infeasible, right? Okay. I'm not going to show you the proof. You can prove this using linear programming duality. But actually, if you look at the history of linear programming, I think Farkas lemma was discovered before linear programming duality was discovered. You don't need linear programming duality to prove Farkas lemma. Actually, you can use Farkas lemma to prove duality, right? So that, but then you can get a very simple proof if you use linear programming duality. Okay. Now there are different variants of Farkas lemma. Right? It's very similar to the different variants you have for taking the dual of an LP. Right? Similarly, you can have different variants of Farkas lemma. You can refer to this page if you want to show a system is infeasible. Okay, so now the last thing I want to talk about, also without giving you the proof, but it's more about how do you interpret this theorem, or maybe in your research when you try to prove something, you can think about this theorem. Right? So this is called the theorem of alternative. Okay. Now, what it says is, suppose we have a system of linear inequalities. It has at least one solution, and D be some scalar. Right? Then the following are equivalent. A is every feasible solution to the system satisfy this linear constraint, right? So this is a single linear constraint. And then B is saying there exists some P such that P transpose A equals to C P transpose B less than or equal to D, right? Apparently, without going to the details, you can recognize condition A is like a primal statement, right? Whenever you have X that satisfy this inequality, it satisfies this single inequality here, right? Then the second condition is like a dual statement, right? You can find some multiplier that certify this inequality is true. So when will you use this theorem? You will use this theorem when you try to show if we have AX less than or equal to B. I want to show this system inequality imply another inequality, right? So if this implies C transpose X less than or equal to D, right? So C and D, C is any arbitrary vector, D is any arbitrary scalar, right? Maybe sometimes in your research you want to show if I have a problem that satisfies this constraint, I want to show if it satisfies this constraint, all the feasible solutions have to satisfy this constraint, right? Maybe this constraint is an easier way to interpret the problem. That's why you want to show that, right? And then how do you show that? The way you show that is find a vector P such that if you aggregate the constraints using P, then this constraint hold, right? Then P is like a certificate to show for if X satisfies this constraint, it must satisfy this constraint, right? Okay, that's where you will use that. But the challenge is that when you need to use that in your research, how do you recognize this theorem? That's sort of the challenge in doing mathematics research, okay? Again, I won't show the proof, but you can show that using linear programming duality, as you can imagine, okay? Yeah, so let's spend maybe 1 or 2 minutes talk about something called dual simplex algorithm. Okay, so last lecture we talked about primal simplex algorithm, right? When you use Groovy to solve an LP, you may recognize there is something called dual simplex algorithm, and then somehow Groovy will choose in a very smart way between primal simplex and dual simplex, right? So what is dual simplex? It is not applying simplex to the dual problem, okay? So it is more like applying simplex to the standard form of the linear program while keeping the reduced cost to be non-negative. So while you keep the reduced cost to be non-negative, trying to move to a primal feasible solution, right? Recall that if you get both primal feasibility and dual feasibility, then you hit an optimal solution, right? And primal simplex is saying we start from a primal feasible solution, trying to move to a dual feasible solution. And dual simplex is the other way around. We start from a dual feasible solution, trying to move to a primal feasible solution. That's a way to interpret that, right? And then you may be wondering, why do we need both, right? So dual simplex is especially useful in solving mixed integer linear programs. I will tell you the reason when we talk about mixed integer linear programs, right? The reason is because the reduced cost doesn't depend on the right-hand side, right? So the dual feasibility doesn't depend on the right-hand side. And in mixed integer programs, we have an algorithm called branch and bound where we are changing the right-hand side of the feasible region, right? So we set x equal to 0, x equals to 1, and so forth. So the primal feasibility will be changed if you change the right-hand side, but the dual feasibility won't be changed. That's why dual simplex is very useful in solving mixed integer programs. Okay, I will revisit that when we talk about branch and bound. And then if you want to know more details about linear programs, you could read this reference. Okay?